So there's another way to analyze circuits besides what we've been doing, which is just sort of using Ohm's law and series and parallel parts. You can use something called Kirchoff's rules. Kirchoff was from the 1800s. I want to say he was German. He was involved in a few projects. One was spectroscopy, understanding the spectrum of atoms. He did some work with a guy named Bunsen from Bunsen burner fame. Anyway, this was an analysis. This was an analysis of circuits and a way to figure out the currents in circuits given the resistors and the voltages. Usually, you're setting things up this way, and you have some resistors, and you want to figure out what the currents are. And sort of the way we've normally done this is we can call this, I coming out of the circuit, or often we'll label this like I1 as the current that's going through the resistor 1, and then we might call this I2, and this I3, right, and then this I4. And there are a few things we can tell. First of all, we could say these two are in parallel, and then this is in series with the parallel of these two, and this parallel of these two is in series with this one. And so we could say, I4 is equal to I1, because whatever current enters this process has to leave it as well. We also know from series and parallel here that since I1 is going in, and I3 and I2 are going out, that I2 plus I3 equals I1. What Kirchoff would say is that this is the junction rule, and the junction rule states that the total current entering a junction equals the total current leaving a junction. So we would say, look, I1 is entering, and I2 and I3 are leaving, and so we would say I1 equals I2 plus I3. At this junction, we would say I2 plus I3 equals I4. Right? In fact, we've already kind of said this, right? We said that since I1 is getting split into I2 and I3, that it equals those two. And similarly, we said the current coming through this into the battery equals the current going out, and so I4 is equal to I1. But Kirchoff would say it in this way. He'd say the total current entering a junction equals the total current leaving a junction. And it's true for any junction, and it's similar to what you would understand if these were pipes of flowing water, or sewage pipes, right? If you have water entering a junction and it splits, then the total water entering equals the total water leaving, and it's the same thing with charges. And so that's the junction rule. And so the next one is called the loop rule. The total change in electric potential around any loop is zero. We've kind of already said this. Look, if I have a voltage increase from here to here of V, and then I have a voltage decrease and a voltage decrease and a voltage decrease, I should get back to zero. So I add V and then subtract I1 R1, subtract I2 R2, and subtract I4 R4, going around this loop. Then I would get back to zero. And so V minus I1 R2 minus I2 minus I1R1 minus I2R2 minus I4R4 equals 0. That's what we say around this loop. And so there are a couple of sub-rules for this, which I'll get. It's true for any loop, so we could pick this loop, or we could pick this loop, and I will write those down in a second, but first I'm going to write the sub-rules. And so I'll call this maybe I, and say when crossing a battery from negative to positive, so going from the negative side to the positive side, we add V. Otherwise, if we're going from the positive side to the negative side, we subtract V. Right? And so when you're calculating the electric potential around a loop, if you go across a battery from the negative side to the positive side, you add V. If your loop carries you around the other way, you subtract V. So that's rule I. And so I'm going to have to erase this now, and I'll give you the next rule. So when crossing a resistor in the direction of the current, so in this case, I picked my current going this way, I subtract I times R. So that it would be, let's say I started here on this loop, I would go V minus I1R1, because I'm going in the direction of the current, minus I2R2, because I'm going in the direction of the current, minus I4R4, because I'm going in the direction of the current, equals 0, because I'm back to my start point. If I was going around this loop, I would say V plus, say I started here, V minus I1R1 minus I3R3 minus I4R4 equals 0. If I was going around this loop, let's say I was going around this loop this way, I would say minus I3R3 plus I2R2, because now I'm going against the current, and that gets me back to my original spot without crossing any resistors again, equals 0. So this would say that I3R3 minus I2R2 equals 0. That would say that I3R3 equals I2R2. But we know that already because these are in parallel. And so the voltage across this one, I2R2, equals the voltage across this one, I3R3. Kirchoff's laws just sort of enforce that. So I'll do a few examples of this on our next screen. So here's an example of a circuit we kind of already did in terms of series and parallel, but now we'll analyze it with Kirchoff's rules. And V equals 12 volts here. And so what I'll do is I'll say, look, the current coming out of here we're going to call I1 because it goes through resistor 1. And the current through here is going to be I2. And the current through here is going to be I3. Right. And so if I know my resistors and my voltage, that means I have 3 unknowns, 1, 2, and 3. And so I have if you remember your algebra, you know that in order to solve for 3 unknowns, I have to have 3 equations. And so right away I get one from the junction rule. At this point here, let me label these joints here: A, B, C, D, E, F. Right. So that's one equation. I could use the junction rule. So if I use the junction rule at B, that's what I get. The current going in equals the current coming out. If I use the junction rule at E, I2 plus I3 equals the current here. But this is just back to I1, since I know that I1 goes all the way around. Whatever I1 is up here, it is down here too. And so it would just give me, if I gave the junction rule at E, it would give me the same thing it's giving me at B, and so I wouldn't get any new information. And so now if now I can use the loop rule. I don't know if this is going to work, but let's try it. So let's use this loop, right? And so we'll use it on, we can start anywhere on it, but let's say we start on at point F. We'll start at point F, and we'll go to A, to B, to E, and to F again, right? And so if I do this, by going around the loop rule, I get V going from F to A, and then the next thing I cross is I1, R1, and this guy is negative because I go across the resistor in the direction of the current, and then minus I2, R2 equals 0. Right, and so that's the loop rule for this loop. I can do another loop. I can do this loop, right, around here. Let's say I do B, C, D, E, B. Right, so here, 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 here. And so B to C, nothing happens. C to D is minus I3, R3. That gets me to here, nothing happens to here. And then plus and so here's one equation. So I now have 3 different equations and 3 unknowns, and in principle at least I can solve this. Right, maybe an algebraic challenge. Let me make a couple of notes here. Suppose we did, instead of this, suppose we went around this loop backwards. F, E, B, A, F, E, B, A, F. Right? So we go F, E, nothing happens there. We get plus I2, R2, because we're going against the current, plus I1, R1, because we're going against the current, and then minus V equals 0, getting back to here. You can see that this is the same equation as this one. Doesn't matter which way I go around the loop, I get the same equation. Okay, and so if I want to wrestle my way through these, I can say, look, I've got these 3 equations, and I want to solve for I1, I2, and I3. So these are the equations that I want to solve from the previous page, and since I have most of these numbers, I can actually solve them in sort of a straightforward way. Let me pick this one first. I can say this says I3, R3 is equal to I2, R2, and so that I3 equals I2 times R2 over R3. But if you remember, R1 is 10 ohms, R2 is 30 ohms, and R3 is 60 ohms. So that just says that I3 equals I2 over 2, or I2 equals 2 I3. And so now if I want, I can substitute into this one. I can say, well, I1 equals I2 plus I3, which is equal to I2 plus I2 over 2, which is equal to 3/2 I2. And now I can substitute that into my third equation, where I can get V minus I1 R1 minus I2 R2 is equal to, so I'm going to substitute in for this guy, and I say V minus 3/2 I2 R1 minus I2 R2 is equal to 0, and so I can combine those, and that becomes V minus, so 3/2 R1 plus R2 times I1 equals 0, I2 so that's V minus, and so 3/2 R1 is 15, so R1 is 10, right? And so times 3/2 is 15, plus R2, which is 30, so it's 45. Sorry, that should be 45 ohms there. I lost something there. Nope. Minor error there, sorry. That's V minus 3/2 R1 is 15 plus 30. The whole thing is 45 times I2 equals 0. And so V minus 45 ohms times I2 equals 0. I2 is equal to 12 volts over 45 ohms, which is, I'll get my calculator. Four 15ths. 0.267. And then based on this equation, that means that I3 is equal to 0.133. Sorry, these are amps. And that means that I1 equals I2 plus I3 equals 0.4 amps. This is a lot of work for a simple series and parallel circuit, but once circuits start to get even a little bit complicated, this is how they're all done with Kirchoff's rules. So when you, in order to set up a Kirchoff's rule problem, you have to pick the directions of the currents beforehand. That's how you know that when you're going the direction of the current, it's a negative voltage drop, and if you're going against the current, it's a positive. So the question is, how do you pick which way the currents go in a circuit? Well, usually it's pretty easy. We know that the current, at least the theoretical current, flows from positive to negative, and so we know how it moves in this circuit. But it doesn't have to be a simple circuit, and you can have multiple batteries sometimes in circuits, and it can be very difficult to tell beforehand which way the current is going. And so fortunately, Kirchoff's rules save you from that. If you remember when we solved this problem in the earlier example on the previous slide, the currents came out 0.267, 0.133, and 0.4, and they were all positive. If you redid this problem with I3 going the wrong way, so that, for example, our loop for this guy, this was B, C, D, E, B, if we went around this way, we would say I3, R3, right? Because if we go around the loop in this direction, we'd be going against the current on this guy and against the current on this guy, plus I2, R2 equals 0, or I3, R3 equals minus I2, R2. rather than I3R3 equals plus I2R2 like we got on the last example. What you'll end up with is I3 equals minus 0.133 instead of I3 equals plus. When a current comes out negative like this, it's telling you that you picked the wrong direction. And so you don't even have to know the directions on these things. Just pick them, and then if your sign comes out negative, it tells you that it's actually going the other direction. If you want to, you can work through this example like we did the last one and see that you'll get all the same answers, but this guy will come out negative if you chose this direction that way. And so it's just saying, hey, flip the direction of that current. That's what that minus sign is telling you.